Hi, everyone. I'm Lloyd Gom. I'm the Global Director of Marketing with the Zappi Group, and I'd like to welcome you to this session. How and why do off-road work sites need to evolve for sustainability? Please remember this session is being recorded and it'll be available to watch on demand following the live presentation. If you have any questions that pop up during the session, you can add them to the Q&A. You'll find that on the tab to the right of your screen. And note that your questions are private. And with that, I'm really pleased to introduce our speaker. I'd like to welcome Dr. Ray Gallant, Vice President of Sustainability and Productivity Services at Volvo Construction Equipment. He'll be sharing his insights on the state of the industry for sustainable power solutions and off-road applications. Really appreciate you being here today, Ray.
Thank you, Lloyd. Good morning, good afternoon, good evening, everybody. Pleasure to be here. Pleasure to have a chance to talk to this subject. It's, of course, a very popular subject nowadays. How do we get to sustainable work sites in other industries other than just automotive or power generation? How do we extend that to other industries? So that's what I'm going to talk about a little bit about today. I'll just flip my screen here. So when I talk about sustainability, I always like to talk and kind of set the stage first as what I mean or what we're talking about when we say sustainability in our industries. So there is a lot of things that go into sustainability, including diversity, inclusion, a lot of social aspects that I won't necessarily be focusing on today that are important considerations. But I view sustainability as basically a balance between three pillars that make up the sustainability envelope. And the first one is the social sustainability. So, are we doing what we need to do as a company to be good for our employees, good for citizens around us, and good for society? So, are we doing our job taking care of the resources that we have access to? Recycling properly, reusing properly to make sure that we leave the world a better place than it was when we began this journey. The second one is environmental sustainability. This is the one that tends to get most of the attention and most of the news, and also has most of the numbers associated with it. So people talk about carbon and carbon neutral and carbon dioxide production, nitrous oxide production, things like that, greenhouse gases. This tends to get a lot of the verbiage in the newscast, but nevertheless, it's only one of the three pillars. So we have to keep the three pillars in balance. And the third one, which is as important, is economic sustainability. So we can do great solutions for number one and two for the social and environmental sustainability. But if they're not economically viable solutions, it won't go anywhere. Companies cannot develop these solutions and then go bankrupt trying to sustain them. That, by definition, is not a sustainable practice. So we have to keep these three pillars in balance, which is the social needs, the environmental needs, and the economic needs. So if you keep that in the back of your mind as I'm presenting, it'll give you a better idea of where I'm coming from and why, there's certain limitations that at this point, with the technology maturity and the social maturity, to be quite honest, we can't get past this point. So we have to view this as a journey, not an endpoint certainly that we're trying to get to, but a journey of how to get there is what we're really talking about when we look at what is the next step. So if I talk about a sustainable site, so we work in construction sites, obviously, and most of them are generally in rural areas. So they're not necessarily downtown in a city next to all the services that we take for granted. Quite often we're 200-300 miles off any location that's got any power or anything else to bring us. So looking at a construction site and comparing it to automotive electrification or general electrification, there's quite a few different considerations here when you start this. So the three steps to sustainability, in my view, are one, we need to have the technologies. So if we don't develop technologies around electric drives or grid-driven machines or even hydrogen-driven machines, we have nothing to convert to. So we'll keep using diesel, we'll keep polluting the atmosphere. We won't come up with a sustainable solution if we don't have products to do it with. So that's basic and the first thing we need to do. The second thing is once you have those sustainable solutions or sustainable products, how do you charge them or how do you refuel them? You know, what is the system and what is the ecosystem that you need around it to get power to it or fuel to it, depending on what your sustainable power is. And this is basically to replace a diesel system or liquid petroleum system that we've had for 100 years plus. So we're not talking a new ecosystem as much as replacing parts of an older ecosystem. We're trying to do it very, very rapidly within a decade rather than 100 years that we've had to develop a diesel system, a diesel infrastructure. And finally, once you get the products and you get the refueling systems or power to the machines and to the site that you need, how can we go about running a much more energy efficient site? And this is really the key to it. And what excites me most about this journey is looking at how we run the site and how we can get much more productive, get the job done with less energy. The reality is diesel fuel is a phenomenal carrier of energy for our application. And it has been over the history fairly cheap and fairly readily available for our machines to use. So as a result, we've become quite wasteful from an energy point of view. So this is kind of a wake-up call to our industry and all the other industries that we have to get much better at what we do if we're going to replace this with other sustainable power sources that don't have the benefits of diesel fuel. For example, if we're to haul 40 tons, today we would fill a fuel tank in an articulated hauler and carry enough fuel to run two shifts, maybe even a third shift with one fuel tank. Well, the reality is you're carrying all that weight of fuel around all day when you don't need it. So is there a way with electric drives where the batteries are very heavy, for instance, is there a way to use smaller batteries and very fast, often recharge and do your work that way rather than carrying around 450 kilowatt hours of energy in tremendously heavy batteries and carrying that around all day and taking away from your payload. So those are the ways we got to be thinking about how we're going to convert these to sustainable sites. There's 5 basic solutions that we see going forward for sustainable power for the first part of those 3 steps I was looking at. So battery electric and the machines for that are already starting to appear on the market. So there are a lot of compact machines from a number of different suppliers that are battery electric driven. And some suppliers have started to move into the mid-level machines now. So we are looking at 20-ton excavators, 5 cubic yard loaders that are battery electric powered. If we don't have battery electric as an option, we can go to alternate fuels. So biodiesels, renewable diesels, they are good options, especially since they're mostly applicable to current machines. So if you want to get your carbon production down on the site today and you have diesel machines, you can switch to a renewable fuel and burn much cleaner from a net carbon point of view than you would with a pure petroleum diesel. If you are in an area where you can connect the machines directly to the grid, which requires the machines to be fairly stationary, that's a wonderful solution because you can draw grid power almost on an unlimited basis and power your machines that way and get the job done. There are a number of hybrid solutions, which is the 4th solution I've got up here. And this is hybrid not only in your power drive, so it could be a small diesel engine running a generator, charging a battery to run your machine, but we could also look at hybrid attachment systems. So instead of running the hydraulics to the attachments and running it that way with all its efficiency losses, why don't we just go electric to the attachment and run electric motor at point and do the attachment that way? So there's a lot of different options there, again, to be more energy efficient in the work we do. And finally, there's a lot of talk in the industry and in the news about hydrogen, either hydrogen fuel cells or hydrogen combustion drives that we could look at as being possible solutions going forward. So those are kind of the 5 solutions and the way we see it uh, appearing in the market. So if you look at those, the next reasonable question would be, where are they likely to appear, to come into the industry, to come into practice? So we look at it basically with a grid where the hours of use per day are along the bottom. So you go from 0 use hours per day up to about 24 hours a day, which is of course the maximum. And the power on the vertical axis, in this chart, it's from 0 to 200, but of course we have machines that use 1,000 kilowatt hours an hour, or kilowatts an hour to do their production. And if we plot the different types of machines that we deal with along those 2 axes, you get a picture something like this. Now, there are always exceptions. There are small, compact pieces of equipment that work much longer duty cycles, and there are large pieces of equipment that work very short duty cycles in certain applications. But in general, this is what you see. The larger the machine, the more the power requirement, the higher it'll be up to the right on the chart. And the smaller compact machines, we generally see shorter duty cycles during the day. They get 2 to 4 hours of generally work hours, and then the rest is idle hours, whereas a haul truck in the upper right-hand corner may be hot operators running 24 hours a day. They just basically, one operator stops, gets off the machine, another operator jumps in, does a quick maintenance check and service check, and goes to work. So they may run literally 24 hours a day with 3 operators or 4 operators. So this is the type of spread that we have, very different than something like the automotive industry, where the average, you're concerned with range, but basically, most cars now are up to a 5-6 hour range limit, which is about what most operators, most drivers are going to want to do before they stop and take a break anyway. So that's a much different duty cycle than some of the duty cycles we have to deal with. So if you look at the very small equipment with a short duty cycle, so low power, short duty cycle, we can do those with battery electric fairly easily. And the small ones, we start with a 48-volt battery electric. And the reason that most of us have gone to a 48-volt is because that is readily available, because the forklift industry, that's what they use. It's scissor lifts, and a lot of these other products are already using a 48-volt infrastructure. So that was fairly easy to go to. If you get to larger machines, then we step up to 600-volt. And this, again, is fairly common when you look at automotive and truck. They're in that 600 to 800 to 1,000-volt range. Now, one of the misconceptions that I deal with all the time is people think that a 48-volt battery or a 600-volt battery, 600's got to have more power. That's actually not true. The reason we go to 600 volts is to get faster charge and discharge rates on the battery. So we can recharge very quickly, or you can draw a lot of power out very quickly. But per pound of battery, you're basically getting the same amount of energy, capability and storage in that battery. And that has very important implications. That's why your power level needed is very important, because if you get, that you need 250, 300 kilowatts an hour, that starts to become a very large, very expensive, very heavy battery. And to the point where you get to a point where that becomes part of your payload. So trucks are very concerned with the battery weight because it takes away payload they could draw. We've got a little bit of more benefit because we can actually use that battery weight to replace the counterweight in our machines. So we're good up to about 250, 300 horsepower. Then we start getting concerned with the room, the cost, and the weight of those battery systems. If you get above that limit, above that threshold, and above about a full duty shift, you start looking at other solutions we think are going to be prominent, including alternate fuels, hybrid drives in that mid-range. If you're able to cable electric or grid connect the machine, that's a great solution. And when you get to the very, very heavy drives, the only viable solution that we see right now is either grid connected electric or fuel cell hydrogen combustion, but basically hydrogen fuel source. And the problem, of course, with hydrogen fuel source is we need the infrastructure. Not everywhere has hydrogen readily available to fill your truck up. So it's basically, you're looking at not only investment in machines, but investment in hydrogen production and hydrogen storage on your facility to run those very high applications. But that is a very viable next solution if you're in that type of application. So where we are on this journey so far, we have basically 6 products in the small 48 volt range that are commercialized. We have a couple more coming out this year. So those are the 48 volt battery electric machines. And then we have 2 mid-range machines, a 20-ton excavator, a 5 to 7 yard cubic loader, that are, again, battery electric machines. We have concept machines in a lot of the other drives. And of course, we do alternate fuels and grid machines in a lot of areas. But these are really what we consider to be the new and emerging technologies, running battery electrics in heavy equipment. And of course, if you have a battery electric drive, you have to provide your customer a way to charge it. On 48 volt systems, it's fairly easy. You can have a plug that charges into, in our case, a 240 or 208 level 2 charger, and will charge the machine overnight. You can even plug it into a 120 volt household outlet. It just takes longer to charge. Or if you're not in an area where you can plug in easily, we're providing mobile power packs where you can charge up the power pack, which is just a big battery, take it out to your machine, plug the machine in, and recharge it that way. And they're available in both level 2 AC charging or level 3 DC fast charging for those 48 volt systems. We also have the same concept with a 600 volt system, but it becomes a little more difficult because of the power requirements. So in the 600 volt system, you can grid connect a charger if you happen to be near enough that your machines can get to the charger, or we look at running battery packs and running them out to the machines, plugging the machines in. And of course, when you get into production machines, the trick is to get them back to work as quick as possible. You don't want it sitting on a charger for 8 hours. You have to get that machine back to work as quickly as possible. So that these chargers are designed, these container chargers are designed to have a lot of power, but also to be able to deliver them very quickly to the machines. So they're a different philosophy than you would have for an automotive charger or a regular grid charger where you're plugging overnight and you really don't want a lot of power going in. You want to trickle charge the batteries overnight. If with both those solutions, they can be hybrid solutions. So we can actually have a grid connector that we take the battery pack to, charge the battery pack from the grid, then take the battery pack to the machine. So that would be a hybrid solution that's possible. You could also do a fully grid connected machine or a fully on-site generation, which would be this picture on the right. So as well as grid connected. You could do a portable power solution, or you could even generate on site and again use a hybrid of the battery packs, the generation, and grid connected to run your job site. So the point is that there's a lot of options because we realize that not everybody is going to have the luxury of rolling their machine up to a common grid point and having that kind of power available that you're going to need to get these machines quickly back to work. So I'll just pause there. So we've kind of gone through a lot of the theory behind it, the solutions that we're working on, and the products that you're starting to see appear in the field, and where we think the next technologies are going to appear. But I want to switch gears a little bit now and actually look at an example of a mid-sized machine that we've had out in the field. We launched this machine about 2 years ago. So we're starting to see enough hours and enough experience with them to see what it really can do and what are the challenges and what are the opportunities with this type of machine. So we did a number of pilots. I'm going to focus on one particular pilot that we did in Southern California. And if you look at that, the fuel was about it, the diesel equivalent to this machine, called a 220E, would have burnt about 4.05 gallons per hour. So that would be its consumption in a normal work over thousands of machines, thousands of different duty cycles. We know that's the fuel it's going to burn on average. The diesel price, in this case, it was $5.29 a gallon. That seems high to a lot of people. They will say, you can get diesel for four something. But the reality is, on most of these job sites, including this one, the diesel has to be delivered on site. So there's a charge per gallon if you work it out for what that costs to run a diesel truck back and forth and refill your machines. In this particular case, it came out to $5.29 a gallon. The industrial electricity rate was 10.49 cents per kilowatt in this particular location. And that's the California rate in this location. That's actually lower than the national average. Again, one of the things to consider here is that we take the incremental electricity rate because the service was already put into this site. So it already had electricity. We were just taking additional kilowatts through the service. So that's the way we viewed this trial. Carbon intensity, we know the California grid in this particular area is 218 grams of CO2 equivalent per kilowatt hour, and diesel produces 10.1 kilograms per gallon of diesel consumed. So that's kind of the basics. And if you look at the chart on the right, we were trying to look at all the sources of greenhouse gases in this, as we have to do when we're talking sustainability. But there's a certain reality when you're talking heavy equipment, is that most of the generation basically comes out of the tailpipe. So it comes out after the machine is produced, after you get it to work. It's when you burn fuel that it really starts to produce a lot of the pollutants that we're worried about. In fact, on an A45, for instance, a 45-ton articulated haul truck, like I have pictured here, only 6% of the emissions of total greenhouse gas emissions come from the manufacturing, the raw material, the extraction, the processing, the build, the electricity to build. All those sources only account for 6%. 94% of the emissions happen after it leaves the factory. So whether it's trucking to a site, whether it's disposing of it at the end of the life, or burning the fuel, 94% of the emissions are at that point. So when a customer comes to me and says he wants help getting his carbon footprint down 30% by 2040 or whatever his particular goal is, I'm not going to achieve that focusing on the 6%. I've got to focus on that 94% if I'm going to get him a meaningful reduction, which is why we spend most of our time worrying about the power source, the energy source, and the energy consumption of these machines and these job sites. So getting back to the trial that we did, so we ran 122 hours in this short trial. If we were burning diesel at 4.05 gallons an hour, and that includes the idle time, we would have produced about 5,000 kilograms of CO2 equivalents. With the electric, we burnt or consumed 4,536 kilowatt hours, which only produced 989 kilograms of CO2 equivalents. And all of that was in the grid electricity, in the grid generation and power generation. So the machines obviously produce no greenhouse gases when they're operating an electric machine, but there is the greenhouse gases depending on how you charge it up. So essentially, if you charge it from a windmill or a solar plant, this might drop to much lower than that, but this is the California rate of the grid electricity. So what that means is at the end of the day, your carbon reduction, your carbon emissions into the atmosphere were down by about 80%. And this is the California case. If you looked at the national grid, it's still down by about 65%. So it makes a significant difference looking at this. Now, a lot of the people, when I talk about this, they say, okay, 10,000 kilograms, that doesn't, I don't know what that is. I don't know what that means. Or, 80% reduction, what does that really mean? So one machine of these excavators is you go electric with one machine, it's the equivalent of about taking about 13 cars off the road or converting 13 cars to electric drive. So if you take the total cost of 13 EVs and balance it against the total cost of one machine to electrify, it's starting to be a pretty good equation in a way to get quick sustainability wins or a lot of progress on your sustainability journey. One of the things that critics will often challenge me on presentations, they'll say, well, yes, but producing a battery and mining and all those things that go into the rare earth minerals that go into your batteries have a heavy carbon footprint. Absolutely true. We're not going to argue that. We're not going to dispute that. In fact, we have about 28% more embedded carbon in an electric machine than we do a diesel. So I often joke about sustainability. If you're going to buy one of these electric machines and park it in your showroom, you've just done worse for the environment than if you had parked a diesel machine in your showroom. And that's the reality of it. Now, the good news is because of the fuel burn, you make that up in about the first 800 hours of use. And by the time you've run about 4,000 hours, which for one of these machines is about just over 2 years, 2 to 3 years, you've offset the entire carbon of the machine, either diesel or electric. So definitely it is more carbon intensive to build these machines. They are more expensive, but the effect over time is quite significant when you start looking at it. So after this, we want to take a look at the economics of it. So, okay, it's great carbon wise. Does it make sense economic wise? And one of the 3 pillars I talked about in the very beginning that we have to keep in balance. So again, in this trial, the 122 hours at $5.29 a gallon, we burned a total of $2,614 worth of diesel fuel through our theoretical twin, diesel twin. The electric machine, 4,536 at 10.49 cents with $476. So your fuel savings cost was 82% per hour. So your cost of operating the electric machine was 82% less than an equivalent diesel machine doing the same type of work in general. So what that means, that's not the entire story. So we know that the fuel savings are there. We know the carbon reduction is there, but we also have other things to consider when you're looking at an electric machine. Our estimate is that an electric machine is going to have about 35% less repair and maintenance. So far in the hours that we've been running these machines, that's proving to be a very conservative estimate. We're actually seeing much higher repair and maintenance cost reductions. And a lot of that is based on the oil and filter changes that you have to do with a regular diesel machine. And of course, you don't have to do or have to do as often with an electric machine. But again, some of the critics will say, okay, your repair and maintenance is down. You got less moving parts. You have less filters, less oils. I buy all that. It's down by 30%. But what about a battery replacement? And that is a very real consideration with electric machines. The batteries do degrade. They do wear out to a certain extent. At one point, they're only going to be good for other applications or what we call second life uses. And they will have to be replaced. So I said, fine. So let's replace an entire battery pack in the machine somewhere during its life and make sure that we take that into account so we give accurate and realistic figures to our customers. And your repair and maintenance savings then drop to about 6%. Okay, still a savings over a diesel machine, but less than the 35% that we were seeing on straight oil and maintenance reduction, fluid maintenance reduction. But then we have DEF in the diesel engines that we have to take into account. And of course, an electric machine, 100% of that is no longer required. So that's 100% savings. So if you plot that out, here's what we're basically looking at. So the assumptions I've got on the left-hand side here. So fuel at 5.29, same as it's been in all the other cases. Electric 10.49, interest at 8%. I said a finance term of 60 months, and I assumed we're financing straight. So no down payment, just 60 months to pay off in full. The delta between a diesel machine and electric machine, I said was 1.7, and that is actually where we are right now. So that's not a number I pulled out to make the numbers work. That's the actual numbers if you compare a diesel price and an electric price today of the 220, 230 Volvos. I assumed 2,000 hours a year. And I assumed that this was with the maintenance and DEF costs included. And if you take a look, you see the line jumps a couple of places, and this is due to the actual repair and maintenance costs we have on the diesel machine through its lifetime. And what's happening is even after you get it paid off at 10,000 hours, then the repair and maintenance starts being more because the machine is, of course, wearing out. So you get parts that you have to replace. So you would think that the curve after you get it paid off, that the curve would sharply decline and you'd only have repair and maintenance. But the problem is that repair and maintenance is going up as the machine ages. So that's what the curve actually looks like drawn from real data that we have from our telematics system. So let's compare that to an electric machine. And here I've assumed battery replacement, complete battery replacement at 12,000 hours. And if you think about that, the batteries, we expect them to be good for at least 3,000 cycles. So that's only a 4-hour duty cycle. So this is a very, very conservative estimate. In fact, we think the batteries are going to be good first life in machines somewhere between 16 and 19,000 hours. Before you'll have to replace a full battery pack. So, but even with this very conservative estimate, what you see is you're basically, from your cash flow point of view, you're equivalent to the diesel all the way up to past that 12,000 hours when you have a little bump when you replace the entire battery. But then very quickly at about 14,000 hours, you start gaining relative to the diesel. And by the time you get to the end of the 20,000 life that we've assumed here, you're about 15% savings on your cash flow over the life of the machine. Just as a frame of reference, this is very close to $1 million in operating costs for a machine like this over its life cycle, over 20,000 hours. So if you're looking at that chart, the electric would be about $150,000 savings on your cash flow over a 10-year lifespan. And if you go one step further and consider that a lot of jurisdictions, you can get incentives to buy an electric machine, This is with a 20% incentives, and you see right from hour one, you're starting to gain ahead on your operating costs. So you're starting to pull ahead and starting to get significant gains. And by the time you get to the 20,000 hour mark, you've saved almost a quarter of your cash flow in operating that machine with the same production rates and the same production that you would have had with your diesel machine. So the economic case is there in the right application, and I stress that it's got to be the right application. These aren't a replacement for every diesel case. We looked at the chart earlier where there's other technologies that might be able to replace diesel in certain applications. Battery electric is not the answer for every application. But if the application is right, it certainly can make economic sense and be viable. So the third step to sustainable power is how do you run your site? And how do you get much more energy efficient? As I alluded to earlier, we've been spoiled by having cheap, readily available diesel, which is a phenomenal energy source. Now we've got to get much smarter at how much we do with every unit of energy we have given to us or have available to us. And when we're looking at this, we're looking at 3 different technologies coming together. And this is where this journey becomes quite exciting to me, because you're combining the sustainable power or the different energy sources that we can bring to play. You're combining that with digital and artificial intelligence and even automation to figure out how we can get the most efficient job sites possible. And to illustrate that, we did a test site and basically electrified a site, what we call an electric site trial. And our goal in that site was to get the CO2 down by 95%, the total cost of ownership or of operation of that site down by 25%, but make sure that we were going at equal production rate to the diesel machines we were replacing. So the site that we electrified, we had one 40-ton diesel loader, we had one 70-ton diesel excavator working on the face, we had a mobile diesel crusher, and we had 3 40-ton articulated haul trucks for a total of 6 units and 6 operators. So we replaced it with a 20-ton hybrid loader, a 70-ton grid excavator. So we electrified the excavator basically to use it. We electrified the crusher. So instead of a diesel engine burning and emitting fumes, we electrified that crusher. We put an electric conveyor in the system as well, and you'll see that on the video, why we chose to do that, and 8 autonomous haulers. So we replaced 6 units that we had before with 11 units of different sizes, different abilities, but only 3 operators. And what we ended up with, and I'll show a quick video here.
Thank you.
Okay, so a few things you might have noticed there. One is that the autonomous haulers were much smaller than 40 ton. They were actually 15-ton haulers. And one of the other things that the video pointed out was they had an 8-minute load and dump cycle. And every cycle they stopped for 1 minute and went to a charge station and took 1 minute of charge to get the batteries topped up again. But what that allowed us to do was run those autonomous haulers with a very small battery, therefore lessening the price of that hauler and lessening the payload, the weight that it had to draw around, therefore lessening the energy. So the end result of this sorry, I had to pick up the share again. So the end result of this, our target was 95% CO2 reduction. Our TCO target was 25%. We actually ended up with 98% CO2 reduction. The only thing producing any carbon dioxide on the site was the wheel loader, the hybrid wheel loader. And again, you'll notice that in the old site, what we would do is basically off the crusher would go into a stockpile. The loader would have to pick it up off the ground in the stockpile, lift it up, load it into the haulers. On the video, you saw why we put that electric conveyor in there, because the haulers could go right behind the electric conveyor and continuously load from the electric conveyor. So the loader then only had to do cleanup and special materials off the site. Most of the loading was actually done with the electric conveyor. Again, a big energy savings. We also saved 70% of the energy cost. This site, the contractor actually generated his own energy, so his energy cost was zero. But what we did in the calculation here is use the grid energy as a comparator. So if he had bought the energy, it would have reduced it by 70% versus the diesel fuel he would have gone through for the same site, same job, and 40% down the operating cost. But one of the biggest benefits of this site, not only did it prove that we could do it and equal the production, but the operators reported, and it was Skanska in this case, reported that this site was much safer way to run their operation than a traditional site would have been. Because when these machines were operating, when autonomous haulers were operating, nobody else was allowed on the site. So the minute, if anybody drove into the site or walked onto the site, the dispatcher would shut down the entire site for safety reasons. And as a result, there was much less possibility of accidents or possibility of human interference or human hazards on this site running it this way. And the people that had to be there were in the cab of the excavator or the mobile crusher or the loader or in the dispatch shack, and not down on the ground working around the machines. So what this proved to us is two things. One, it can be done with the technology today. It can have significant benefits. And two, that the key to a sustainable site is actually in the energy management. So we can do a lot of things to improve the site, to improve the workflow. But if we focus on energy management, we can get it to a sustainable point as well, and meet the goals of sustainability and the targets that we had set. So with that, I want to close with a quote that I love from Senator Tim Scott, Republican from South Carolina. And he said simply, faith in the future gives us power in the present. So if you think about that with today's situation, basically, we have the people that can solve this. We know how to do it. The technology is maturing. It is there. if we have faith that we will get there, we will have the courage and the ability and the bravado to take the steps that we need to do in the present to make it happen. So I'm very encouraged by what I'm seeing in general. And with that, I'll turn it over if you have any questions that you want to pose.
Well, thanks, Dr. Gallant. That was a really good presentation, really helpful. I have a number of questions. We've got about 10 minutes. Here's one on the TCO calculation. The audience member says, very interesting, the TCO calculation is in favor of electric. If we also consider carbon emission savings, he was wondering why for the OEMs, it's sometimes hard to convince users to go electric.
The biggest issue, well, two issues in my opinion that is hard to convince. One is a change in how they do their operations as well. Like, it's not only getting an electric machine, you have to have the charging systems, you have to have the schedules adjusted. You know, you don't want trucks showing up to be loaded when you've got your machine parked on at a charger. So there's a lot of other changes that have to take place, as that video illustrated, to really take advantage of these changes that have to take place. A lot of contractors are also looking at the initial cost, and you know, from a finance point of view, that is a big, 70% cost increase is still a big nut to swallow. So one of the things that I see happening already in the industry is we're starting to see finance companies step up and come up with other ways of financing sustainable equipment. So giving a higher residual on a battery, because a battery that's not suitable for electric equipment may be perfectly suitable as a backup for a wind farm or a solar field, or a battery pack, even a charging pack. It might be perfectly suitable for those applications because you can trickle charge and trickle discharge, which is much easier on the battery. So we replace the batteries. We consider it at 80% they need to be replaced. They may be good for other applications to 30 or 40%, which may buy them another 10 years use. So finance companies are now starting to come up with formulas that give the customer credit for that battery, or that core, if you will, that make the financing much more attractive. But until those things mature, how we operate with these electric machines and the financing around them, it's still a pretty hard sell.
Understood. Thank you for that. Another question is probing hybrid solutions. The audience member question is, according to your experience, is that parallel hybrid solution viable to reduce consumption of diesel and emissions when the machine power is in the range of 250 to 550 kilowatt? He goes on to say smaller diesel engines than a normal application could be used, and the electric motor would be boosting the crankshaft rotation when higher power and torque output is required.
So in my experience, yes, and that is the range that I'd say it's very feasible. And you get a big benefit because you're running a much smaller diesel, and you're also able to run it in its sweet spot in terms of emissions and power. So it's much more efficient than having to cycle up and down from low RPM to high RPM when you need power or torque. So with a hybrid, you're able to run the engine in a much better range for both emissions and power and fuel consumption, and therefore, and use your electricity battery backup as the boost when you need the high power. So in my experience, yes, it's a very good solution if done properly.
Okay, thank you for that. I think you might have answered this. Well, we touched on it. Another audience question. For the repair and maintenance cost to drop to 6%, did you consider the second life of the battery? Um, or do you consider the price of the used battery?
Yeah, so what we've said is we're expecting 35% diesel to electric comparison just because of the fuels, the oils, and the wear parts in a diesel are much more than in electric. The 6% came about because we replaced an entire battery pack at 12,000 hours. So that brought it down from 35 to 6% cost savings.
Excellent. Thank you. I think we got time for one more. This one says, when you work on electrifying a machine, do you take a holistic approach, and take care of the role that each component plays in the machine? In particular, what is the role of hydraulics in an electrification project, or are you focusing uniquely in the internal combustion engine? I think you spoke a bit to that.
Yeah, and I spoke a bit to that when I talked about hybrid. So we are very interested in electric attachments as being a way to get the energy use down. The issue there, of course, is there's millions of hydraulic attachments in the field already, and we want them to fit electric machines and work properly. So for a while, you'll be seeing both hydraulic and electrical attachments being possible on these electric machines. But in the future, I think it'll be more and more electric attachments just because they're more efficient from an energy point of view, and you'll be able to conserve battery power, if you will, and get a longer duty cycle. The other, we spoke about overall efficiency. Most machines out there, in fact, all machines out there that you're seeing commercialized, basically are replacing the diesel engine with a battery pack and electric motor. And then we do a lot of tuning to make it act exactly like the electric, or exactly like the diesel. So the operators are comfortable jumping from one to the other. The second and third generation machines, what I see happening is we're going to start designing more around the capabilities and opportunities around electric drives. So the fact that you can have a motor at a very high RPM in some duty cycles is advantageous. The fact that you have instantaneous torque from 1 RPM, all those features means you can start changing the machine design to take advantage of those and produce much more efficient machines, but they're electric only designs. So if you look at our diesel machine today and the electric version, 70% of the parts are in common, which is good for the operators because they have parts on the shelf that'll fit either machine. It's good for us because we can supply parts and service easily. When you get to these new machines, they'll be much more efficient, a much more productive point of view for designing around electric, but it's going to take a while for the parts, the aftermarket, everything to catch up to those new ways of doing things.
Okay.
But that's part of the evolution and part of the journey. So, as I
Right.
said, sustainability is not an endpoint, it's a journey.
Yeah, that's well said. Just actually one more question.
Mhm.
You have a time, but this will be the last one. This is a battery related question. What's the preferred battery chemistry for Volvo for electric construction equipment?
We use NMC or NCM and LFP batteries, so we have both chemistries in our machines. Either chemistry has both its advantages and disadvantages. As everybody probably knows, we haven't settled in on one, and there are others emerging. We're looking at sodium batteries, we're looking at solid state batteries. So time will tell, but right now we use both the major chemistries in our machines. Again, depending on the machine design, duty cycle, we try to pick the best battery chemistry and package that will do the job in the best way possible.
Excellent. Well, thank you for, I didn't get to all the questions. So I see your contact information is presented there. So can users follow up directly with you or audience
Of
members?
course,
Questions? Okay.
feel free to contact me directly and I'll help in any way I can.
All right. Well, thank you very much, Dr. Plant. Really appreciate the presentation. Really top of mind for us in Zappi and customers, partners, battery partners, all of that. It's all very relevant. Thank you so much.
Thank you very much. Pleasure to be here.